אנחנו עוברים על כל התמורות, כל תמורה תורמת. Right, I forgot. So we're going over all the permutations. Each permutation contributes one. Sorry about this, and we get n factorial, which is very much different from what the determinant is, because the determinant is 0, right? We have cancellations with the determinant. We don't have cancellation with the permanent, so it's kind of easier, right? It's nice. We are summing without signs. Should be easier to deal with. The truth actually is that there are not so many matrices for which we do know what the permanent is. It's kind of hard, and basically, sort of, these are the two matrices we know the permanent, and up to some, small number of examples, these are the only two matrices we know the permanent. I'll give some more examples, but that's not so easy. Right, so to make it easier, slightly easier to know how to compute the permanent, how to understand it, let's discuss the connection of permanence to counting, which is a very sort of strong connection. So if our matrix is a 0-1 matrix, which is the adjacency matrix of a bipartite graph, so I have I in row I and 1 in row I and the column J, if and only if vertex I on the left is connected to vertex J on the right, then permanent is exactly the number of perfect matchings. So it's a nice notion with a combinatorial meaning. Has some applications. Let me say some good words about the permanent. It's nice to know how to compute it, because if the graph is a grid, just a regular integer grid, it computes the energy, the permanent, the number of perfect matchings, equals the energy of some system in some well-known physical model. So we want to be able to compute the permanent. And in fact, not only counting perfect matchings, this is something that we know to do how to compute. If we know how to compute the permanent, we can do more surprising things. So many papers by Barvinok and two papers, one by Friesen Krivelevich from 2005, one by Ferber, Krivelevich and Sudakov from 2012. For instance, there are many more examples show that if we know how to compute the permanent, we know how to count other things, not only perfect matchings, but Hamiltonian cycles in a graph, contingency tables, which is something that comes from statistics, tables with integer values, with given row and column sums. We want to know how many tables like that there are. We can count them if we can compute or approximate the permanent. So fine. So permanent counts perfect matchings, and this tells us that we can actually compute permanence of 0-1 matrices with at most 2 ones in each row and each column. Everything else is 0. Because it's a graph of degree at most 2, it decomposes into a disjoint union of cycles and paths. This we can do. So here is one example. This is the permanent of one large cycle of length 2n. There are two matchings. The permanent is 2. Here is another example, another large matrix. This is a union of n over 2 4 cycles. And it's a disjoint union. And there are many matchings. There are 2 to the n over 2 matchings. So note that we have two matrices with the same value distribution. We have 2 ones in each column and each row in both matrices. The gap is basically 2 to the n over 2. And there is a conjecture that this is the largest possible for two matrices with the same value, the same distribution of values. We'll get to that in the end. Okay, so now we sort of think that computing the permanent is good. Let's try to compute it. So the easiest way, just by the definition, we sum over all the permutations, is basically it will cost us n factorial. We can also do something smarter, a version of the inclusion-exclusion formula, which is known as Reiser formula, which gives us a simple exponential algorithm, costs about 2 to the n, but we can, we want to do it faster. So this is an old question. It starts from Poya, or maybe even earlier. So Poya suggested trying a similarity to determinant. So what can we do? We can take a matrix. We know how to compute the determinant, right? It's easy. We can add signs to the entries. We add signs to the entries. We sort of, it's like turning the permanent into the determinant. It turns out to be impossible. Poya by himself noticed that this is something which won't help even for 3x3 matrices. He gave an example. And then people, of course, tried to do smarter things, to use any linear forms of the entries. We get a n by n matrix. We want to compute the permanent. we replace each entry of this matrix by a linear form in the entries of the matrix. Maybe it helps. Well, it doesn't. This is a result by Marcus and Mintz from 61. Another, an even stronger change to the matrix, we can take a larger matrix, right? With with entries which are linear forms in the original matrix. And this, this is not an easy question to show that we cannot do it, actually. And Mignon and Rassay in 2004 showed using topological methods that one cannot do it even if one blows up the size of the new matrix to be squared, like n squared by n squared. Of course, the conjecture is that we have to go exponentially high to get the permanent. Okay, and this is because Valiant in 79 showed that permanent is sharply hard to compute. Sharpy is the strong complexity class. So if you know how to compute the permanent, we can, for instance, find the number of satisfying assignments to any Boolean formula. So it's hard, and it's even hard for 0, 1 matrices with 3 ones in row and column, right? So 2 ones we can do, 3 ones we cannot do already. And, so the permanent is very good at counting things, right? If I can compute the permanent, I can compute anything I want, which shows it's probably hard to compute. So the next natural question is, of course, can we approximate the permanent? And the answer is yes, we can. This is a result by Jerome, Sinclair, and Vigoda from 2001. But before we get to that, let's go into the more natural direction, ask about even harder matrices, right? So we know we cannot compute permanents for 0, 1 matrices with 3 ones in a row and a column. What about more general matrices? So, it seems hopeless, at least at this stage of our knowledge. We don't know how to approximate it, but it's interesting. It's interesting, for instance, a conjecture due to Aronson and Arkhipov says that it's hard to approximate the permanent of a random Gaussian matrix, to approximate up to a certain factor. And it's important to show this because then we'll show that quantum computers cannot, in some sense, be simulated by classical computers. So it's an interesting question. Right. So now mostly this talk will be stories about the permanents. It's a long history. I'll start from some very old history. So permanent is a natural object. I hope you agree. It's like the determinant, without the signs. It has combinatorial, meaning counts perfect matchings. A very nice object. So people looked at it for a long time, starting from 19th century, starting from Binet and Cauchy. It's not quite clear to me why they looked at it, but it seems to be, it's like a multilinear function. It's a permanent. It looks like the determinant. One can say things about it. And right, so people proved some simple things about the permanent. On the other hand, it should be somehow hard to prove, more complicated things about the permanent because it sharply complete, right? It shows that it lacks the mathematical structure of the determinant, right? Determinant is extremely structured, right? It has this meaning of computing the volume, and this basically sort of simplifies the algorithmic computation. We have a polynomial computation. Permanent seems to be lacking all the structure. So it has to be hard to deal with mathematically also. And this, in fact, shows up in the 20th century already. It turns out to be very easy to ask mathematical questions about the permanent, to conjecture conjectures, because as opposed to other cases, all the extremal examples are usually either I, the identity matrix, or J, the all-one matrix, or just block matrices, which are small copies of J's and I's, right? But it's very hard to prove these things. So for instance, here is a conjecture attributed to van der Waarden from the 20s. He considered doubly stochastic matrices. These are matrices with non-negative entries for which every row and every column sum to 1. And he asked what's the minimum of the permanent on this set of matrices. It's a very nice set of matrices. He conjectured that this very nice matrix, a flat matrix, 1 over n in every entry, has a minimal permanent. It's a very easy question. It's an optimization problem. One can try and solve it, but it turns out to be kind of hard. Another conjecture from the other side about upper bounds on the permanent comes from Mintz in 73. And the question is as follows. Suppose we are looking only at 0, 1 matrices, and we know the number of ones in each row. So we are looking at a bipartite graph, and we know all the degrees from the left. We want to have the maximal permanent or the maximal number of perfect matches. So means conjecture, that's the best we can do it. You can sort of arrange your entries, your metrics, to be as close as possible to the block diagonal matrix. This was a conjecture. Again, it's kind of easy to conjecture and hard to prove. So the van der Waals conjecture turned out to be true. It took 60 years to prove it. And there are all sorts of stories around this proof. But anyway, it's not easy, and just looking at the optimization problem and trying to use local constraint doesn't work. Actually, Igorchian and Felikman, in different ways, used deep mathematical tools, a deep mathematical tool, which is the Alexandrov-Fenchel inequalities from convex geometry, a complicated tool. And the conjecture of means also turned out to be true. Took only 10 years to prove it. This was proved by Bregman in 73. And the proof of Bregman is also very non-trivial. Some easier proofs were obtained later. In particular, he uses convex optimization, which is not obvious, right? Why would you use convex optimization here? And along the way, he invents metric scaling, which is something I'll get to. You take a matrix, it turns out that for any matrix with some reasonable pattern of zeros, you can multiply any column by a number, any row by a number, and get a doubly stochastic matrix. This is something we will also use later. And Bregman uses it in his proof and does some other non-trivial things. Okay, so first of all, note that these bounds, we have upper bound on the permanent, we have lower bound on the permanent. Both of them are for restricted classes of matrices. We have a lower bound of Igorchian and Felikman for doubly stochastic matrices, and upper bound for 0-1 matrices. If you want to estimate a general matrix, we need to do something. It turns out that the lower bound is not a problem. One can use metric scaling effectively to get from any matrix to a doubly stochastic matrix, from any matrix with no negative entries. The upper bound is more of a problem. We still don't have a good generalization of Bregman's bound to a general matrices. Okay, so bounds for restricted classes of matrices, easy to state, but hard to prove. Right, so now we're getting back to this question of why do we want to approximate the permanent? We definitely can't compute it, so why is it interesting? So I'm just repeating the things I said before. In physics, it computes energy of some systems. Physicists really want to compute it. In quantum computing, this goes, if we know how to prove the conjecture of Aronson or Hipov, we would know something about non-simulability of quantum computers by classical ones. In theory of CS, right, so we have this natural counting machine, the permanent, and obviously, again, we probably can't compute it, but it would be good to approximate it, right? And then it's a very nice matrix function. It's a multilinear function, right, which goes into this random self-reducibility of the permanent. It has all this nice structure. It's easy to deal with. And it looks deceptively similar to this very nice, really very nice function, which is the determinant, which is efficiently computable. So there is some mysterious gap between the two, and we want to be able to deal with it. And in mass, right, so this hardness of computation, this hardness of permanent, shows there is a definite mathematical mystery in this. And the question is, can we use the classical bound? We have this of Igorchian, Felikman, and of Bregman to try and approximate the permanent, to know things about the permanent, or maybe can we along the way discover new bounds? Since the permanent, as we will see, turns out to be approximable by a non-explicit randomized algorithm, right? There is a randomized algorithm, which I will describe briefly, which gives us the value of the permanent. It sort of should tell us that there is some structure we still don't know, still want to discover. All right, so what's, we are speaking about approximation. What are the notions of approximation we want to describe? So the first one is sort of the usual multiplicative approximation. We are given a non-negative matrix. We want to compute an efficiently compute a function of this matrix so that the permanent is between a function f of a, so the permanent lies between f of a and some constant times f of a. This is the multiplicative approximation within a factor of c. This is one notion which we are going to discuss, and another notion is like explicit bounds on the permanent. The first notion is also explicit. I want something even more explicit. So what do I mean by that? Given a matrix A, I want to know what the permanent is, just by looking at it, right? And I'm using this word divine, divination is complicated, so what do I mean by that? So here is an example of something I would like to be able to say in higher generality. Suppose we have a doubly stochastic matrix. Every row and every column sums to 1, so suppose it's kind of a random matrix. We just chose the entries at random between 0 and 1 and normalized the rows and the columns. So all the entries will be bounded by a constant over n. K, think about k as a constant. Then it turns out that we already know that the permanent is between e to the minus n and some polynomial, some n to the k prime. K prime is another constant depending on k times e to the minus n. So just by looking at this typical matrix, we know what the permanent is, up to a polynomial factor, which you don't care about usually. So this is something we would like to be able to say in higher generality. This follows from combining the lower and upper bounds of Egorov and Falkman and Bregman in a slightly non-trivial way, and this was observed by many people, several versions of this double inequality. It was observed by many people, this understanding that given a slightly restricted class of matrices, we know the permanent up to a small factor. And again, it seems to be observed by many people independently. Apparently, the first person I know who did this was Noga this is what Nati said, in the late 80s, that there is, if we restrict the entries in some meaningful way, we sort of know the permanent up to a smaller gap than we would have supposed to. We would have guessed, and this goes into all this usefulness of permanent for counting contingency tables and and Hamiltonian cycles and so on. Okay, so so this is something we would like to be able to say. So just to say it again in a different way, so most permanents are very easy to estimate, up to a small factor. But this somehow depends on what do we mean by the notion of most. So suppose there is a situation which would be in which it would be very useful to know what is the permanent of a matrix obtained by choosing every entry at random according to the simple exponential distribution, right? With parameter 1. So in every row, and then sort of normalizing it to be doubly stochastic. So in every row, we'll have one entry of size log n over n, basically. And if we have this, then this combination of lower and upper bounds already gives us a super polynomial gap. It's clear that the permanent of such a matrix also should be polynomially close to it is a minus n, okay, but it's a guess. We still don't know how to prove it. Okay, so it's right. So now we are switching from back to history. We described very old history, starting from 19th century, mathematical history. Mathematicians dealt with it. Now we are going to computer science, and we start with trying to approximate the permanent. Attempts to approximate, and the first, somehow historically, the first attempt was to use the similarity between the permanent and the determinant. This goes back to Gotzel and Gutmann, sometime in the 80s. And here is a very simple observation. We have a matrix with non-negative entries. We take a square root of each entry, and we multiply it by epsilon ij's, where epsilon ij's are independent random variables with expectation 0 and variance 1. It's a new matrix, and it turns out it's a random matrix. And it turns out that the permanent is the expected value of the square of the determinant of this matrix. Now, this is very good news, right? Random matrices is a very well-developed area of mathematics. We know a lot about it. And we just want to say that, and we want to estimate the expectation of a square of the determinant of random matrices. Determinants of random matrices, again, it's a very well-studied notion. So basically, we have a random variable. We want to estimate the expectation. We just need to show that this random variable is reasonably well concentrated around its mean. The problem is it's not true, right? So usually. So, one has to work hard to show something, and it started with Gotzel and Gutmann, and then Karmarkar, Lovász, Luby, and Lipton several years later. So both of these groups of researchers, they took epsilon ij's to be roots of unity, random roots of unity. Gotzel and Gutmann took plus minus ones, and KKLLL took random third roots of unity. It turns out that in both cases, the the variance is rather large, so it doesn't work very well. Barvinok in 96 took epsilon ij's to be Gaussian. And it turns out that this already gives an exponential type approximation. So basically we get this function f of a randomized function but efficiently computable, such that the permanent lies between f of a and c to the n times f of a, where c is about 4, right? So at this point in time, we get a 4 to the n approximation for the permanent in 96. Right, so this is one direction. The other direction, which turned out to be more fruitful, is the Monte Carlo Markov chain method, which is a very well developed and very well known method in approximation. And it started actually with this question, with the question of approximating the permanent. So the person who suggested this method was Broder in 86, and he said that in this particular instance, if you have a random walk, if you define a random walk on perfect matchings of a given graph, and we can show this walk to converge rapidly to uniform distribution, we would be able to sample from randomly at uniform, approximately at uniform, from perfect matchings, and then we would be able to count them approximately. This is very easy. If we can sample, we can count. Right, so Broder's original paper had some errors, which were corrected in the follow-up paper by Jerome and Sinclair, who introduced a better random walk. It turns out that walking only on perfect matching is not good enough. One needs to walk on a larger set of perfect matchings and nearly perfect matchings. And they introduced tools for proving rapid convergence of random walk in all these large combinatorial Markov chains, which of course, turned out to be very useful for many other things as well. But they did it in 89. They had it for some partial families of graphs, not for all graphs. And this will be continued, about 10 years later, together with Vygoda, they gave a complete solution to the problem. But I'm speaking about old history, and this would be new history. Right, so, and the third direction is combinatorial bounds. And again, we come back to doubly stochastic matrices. A doubly stochastic matrix is a matrix, with rows and columns assigned to 1. If a matrix is doubly stochastic, its permanent is at most 1. This is very easy. The permanent of a non-negative matrix is bounded from above by product of row sums. This is trivial, so it's at most 1. And also by the Gorbachev and Falikman bound, it's at least e to the minus n. So for a doubly stochastic matrix, we already know, just by looking at the matrix, we already know the permanent up to this multiplicative gap of e to the n, which is smaller than 4 to the n, right? This is a lucky thing, e is smaller than 4. So we get an e to the n approximation if only we can reduce a general matrix to the doubly stochastic case. Turns out this is not completely trivial, but this could be done efficiently, and this was done in a joint paper with Nati Lineal and David Vigdorsson in 98. So at this point in time, in 98, we were the champions. We knew how to approximate the permanent up to e to the n by a deterministic algorithm. So unfortunately, it didn't hold for too long. In 99, Barvinok took epsilon ij's to be complex Gaussians and quaternion Gaussians. So, you look at more complicated Gaussian models, and this gives a better approximation. Already gets C to be 1.3, which is smaller than E. 1.3 to the n, I guess, since I'm thinking about the factor. And then Jerome, Sinclair, and Vygoda in 2001 solved the problem. They gave a complete approximation scheme for the permanent of a negative matrix in a very interesting result. So they have a walk with weights, not on 0, 1 matrices, but actually on general matrices somehow. And it works. And right, so the problem is solved, and this is like end of history, right? They're done. But so still, there are some stories to tell, and this is a post-history. Turns out there is this notion. I found it on the internet. There is post-history in historical studies. What happens after the humans die? So right. So post-history, one can use more complicated Gaussians. I'm talking about the Monte Carlo Markov chain method is has won the field, right? So I'm not talking about it anymore. It did what it wanted to do. We're talking about the other two methods. So using determinants. So one can use Gaussians. So one starts from real numbers, complex numbers, quaternions. There are all sorts of algebraic structures, algebras, more complicated algebras, continuums. There are Clifford algebras, It turns out that one can use Gaussians based on Clifford and elements in Clifford algebras, whatever this means, and these new structures, these new matrices over these algebraic structures, their variance gets smaller and smaller. And actually, if one goes far enough, one gets a very small variance, one can approximate the permanent. The only problem is I cannot compute the determinant. Right? So this is an open question. And this was posed by Barvinok somewhere in the early 2000s, and Chien actually wrote a paper about this in 2005. And in fact, there was also a paper who solved this question by showing how to compute the determinants of Clifford, matrices based on Clifford algebras, but the paper was wrong. It had a hole in it, so we still don't know how to do it. And then, experts in random matrices still try to show that Barvinok's algorithm works at least in some cases, and there is a relatively recent paper by Ruderson and Zeytouni that shows that the algorithm of Barvinok does achieve a very good approximation on large classes of graphs. The variance of this determinant squared is small. So going to the combinatorial bounds, Leonid Gurvits in 2006 gave a very nice proof, a beautiful proof of lower bounds, of the Gorbachev-Felikman lower bound on the permanent, using a very different mathematical technology called hyperbolic polynomials. And in fact, this led to many extensions and applications. In particular, this is apparently an important ingredient in this famous work on the solution of the Caddison-Singer problem, recent solution. Right? And from the other side, there were two papers giving new upper bounds of the permanent. So there was a paper by Carlen, Lieb, and Loss in 2006, and a paper by myself in 2008. Both papers were done in 2005, but these are publication dates, independently, and this gives an upper bound on the permanent, which seems to be similar to a Hadamard inequality for determinants, right? The inequality of Hadamard for determinants tells us that the determinant is smaller or equal than the product of the L2 norms of the rows or the columns, right? This is the inequality, and here we can show that the permanent now, not the determinant, is bounded by a product of some norm of the rows, some norms related to the LP norms. And the natural conjecture that comes independently in both these papers, so here is a simple question, right? How can we maximize the permanent if we allow to choose its rows to be unit vectors in LP, right? If P is 1, then these are just stochastic matrices. A unit vector on L1, of course the entries should be non-negative to maximize the permanent. So get stochastic matrices, the optimum is attained on the identity matrix. This is very, very easy. What happens for P greater than 1, right? So I'm giving you allowed, your rows are unit vectors in L2, right? How can I maximize the permanent? It turns out, so it's not clear, right? And it turns, because it's not clear what the obvious candidates are. And it turns out there are no new candidates. So the conjecture is it's either the identity matrix normalized or the all one matrix normalized. We cannot prove it. We are somehow close to it, but not completely. But note this mysterious thing, right? There are only two examples. Either the identity matrix or the all one matrix, although this problem sees to be very different. Right, and I think the intuition of CLL was they come from analysis. They had all these methods to prove Hadamard type inequalities for different mathematical structures. They wanted to extend it to the permanent. So for me, the observation was, so it's not clear how to extend the upper bound for 0-1 matrices due to Bregman to general matrices, and one way to try and extend it is to see that it's actually kind of an Hadamard type inequality. I don't have time to explain it, but one can think about it this way, and this leads to bounds of this type, and turns out reasonably useful. Okay. So finally, I'm getting to results on this talk. I have zero left. Okay, so I have like about 30 seconds, I guess, so maybe 1 minute. Okay, so the deterministic approximation algorithm scales the matrix to be doubly stochastic and stops. We look at it and we get e to the n approximation. We want more. We want to be able to compute a nice function of this matrix and to say that we get some information on the permanent. This is what we did in a joint work with Leonard Gurwitz 2 years ago, and this is a very nice function. It's the product over all entries, 1 minus the entry to the power 1 minus the entry. It's like the exponent of the entropy in some sense, right, or something. Somehow related to the entropy. Turns out there is a lower bound. Permanent is always greater than this, and there is an upper bound. Permanent is always smaller than 2 to the n times this. So this immediately gives 2 to the n approximation. I should say that it should be possible to get basically to 1/2 to the n with the same methods, but probably not more than that. And let me just say a couple of words about the techniques, even not the techniques, just sort of the flow of the things. So the lower bound was conjectured in the statistical physics community by von Tobel, who actually gave a proof, but the proof turned out to be not correct. And the proof uses, one just writes out optimality conditions. This is an optimization problem. As usual, for the permanence, this is not enough. And then one has to do something more. One has to use another famous lower bound of the permanent due to Schreiber, and then things work out. And it's essentially tight for all the usual matrices, for I, for all one matrix, and so on. And it has several applications in statistical physics, proves some conjecture of Friedland, and so on. The upper bound is it actually follows from another Hadamard type inequality. Permanent is bounded by a product of some norms of some norm of the rows. These norms are Orlich norms, which I'm not going to talk about. They're sort of generalized LP norms. They are based on some convex function from 0, 1 to 0, 1. LP norms come from x to the p, from the monomial, but one can take other convex functions, and this function has to satisfy certain properties. One should find such a function, but everything works, and we get the upper bound. And the last slide, the open problems. A conjecture due to Gurwitz says that this permanent actually should be bounded by 2 to the n over 2 and not 2 to the n. This would be tight due to the example of these 2 large matrices with 2 ones in every row and column I gave at the beginning. Here's another conjecture, and then I'm done. This would be very nice and useful. Suppose you have a double stochastic matrix such as the L2 norm of the matrix is a constant. The sum of the squares of the entries are bounded by constant. Then the permanent is at most some polynomial in n times e to the minus n, and that's it. Thank you very much.